Good morning, everyone. Good morning, sir. I am Jade Brian Sultan, and together with my co-reporters, Jerry, Faith Nino, and Princess Girly Oliveira. And this time, sir, we will report to you about refrigeration. So let's talk about vapor compression refrigeration cycle. So it is also known as the direct expansion DX refrigeration cycle. It's the method of transferring heat from low temperature region to a high temperature region, essentially driving heat in a direction that is opposite to its natural flow. In this process, the refrigeration or cooling segment of a building or air conditioning system absorb heat from within the building and transfer it to the outside. So, from inside the building, the heat will travel through the fan and will release outside the building. For example, in a refrigerator in our kitchens, the heat removes from the ice box and discharge it outside the refrigeration cabinet. If vapor compression refrigeration equipment is used in most building to that space cooling capabilities. The vapor compression refrigeration process is used in most building air conditioning system. Room air conditioner and central air conditioning system found in homes and light commercial buildings cool using this process. So large commercial buildings use chillers and water towers that rely upon the vapor compression refrigeration process to generate chilled water cooling coils and air handling units to distribute the cooling effect to the building space. For example of this is we can found in malls. The next slide is this is the diagram of a component and process of vapor compression refrigeration cycle. So the motor fan is attached on the room. It will where the heat will be removed and get inside the evaporator. Then it will process a warm temperature and low pressure gas, and it will go to the motor driven compressor. Then the compressor will compress the gas and when it compresses the gas, it releases high pressure gas and also high temperature. And then the motor driven fan will release it in the heat outside the condenser. Then in the condenser, medium temperature high pressure liquid will go inside and will go to expansion valve, and up from the expansion valve, low temperature low pressure liquid will go back to the evaporation and will release cold air, and then the process goes on and on. A refrigerant is a substance that produces a refrigerating effect while expanding or vaporizing as it circulates as a gas or liquid through a closed vapor compression refrigeration system. So example sa refrigerant is karang freon on our refs bitaw. It picks up heat by evaporating at a low temperature and pressure and gives up heat by condensing at a high temperature and pressure. A good refrigerant must absorb and release heat readily, high latent heat or vaporization, be easily converted from a gas to a liquid, be relatively non-toxic, and have good lubricating qualities. Properties of refrigerant are provided in table 6.7. So these are the properties of the refrigerants. Heat of vaporization on British unit and global warming potential, and also the ozone depletion potential. So it is found on table 6.7. Ammonia is a good example of a low-cost refrigerant which has a good heat transfer properties and thus good efficiency. It has been used extensively for industrial refrigeration application and is being developed for commercial air conditioning, mainly in Europe. Ammonia is highly corrosive, and the copper-based alloy used in conventional air conditioning system, more expensive stainless steel tubing or aluminum is needed. Ammonia is moderately flammable and toxic, so it is delicate to our health. Ammonia system must use open drive compressor, which result in some refrigerant leakage. Therefore, Because of safety and reliability issue, ammonia is not being considered seriously for air conditioning application in United States. So in United States, it is already banned and not considered to be safe. So the next slide is about evaporator. The evaporator is a network of tubes filled with refrigerants located inside the building that absorb heat from air or liquid and move it outside the refrigerated area by means of refrigerant. So the evaporator is the one responsible for removing the heat in the rooms where air condition is being attached. In a split air conditioning system typically used in light commercial and residential application, the evaporator is a coil network of tubes located in the plenum ductwork near the furnace. The furnace serves as an air handling unit, blowing air across the coil where it is cooled and delivered through ductwork to the indoor room. So ductwork is the one who releases the cold air. It is also known as a cooling coil, fan coil, or indoor coil. In large commercial installation, the evaporator is part of the chiller. For example, is kanang nasa orama sa ilang chiller, maupo na ilang aircon. So it is part of the chiller mismo ang ilang air conditioning system, where it is cools chilled water that is piped to cooling coils located in ductwork. Next is the condenser. The condenser is a network of tubes that discharge unwanted heat from the refrigerant to a medium. Example, air, water, or combined of air and water that absorbs the heat. As the heat is discharged, the refrigerant condenses and becomes liquid again. So for example, when the room is so hot, the condenser, it absorbs all the hot air and convert it to liquid again. There are three types of condensers: air-cooled, water-cooled, water-cooled, and evaporating condenser. The air-cooled and what is usually typically used in residential application. The water-cooled is usually used in large applications such as malls, and while the evaporative condenser uses both water and air on its application. Next is the compressor. It is a pump-like device that drives the refrigerant from the indoor evaporator to the outdoor condenser. So we must always remember that the evaporator is always inside the room and the condenser is outside the room. So between the two, before air passes through the two said things, it will first travel to a compressor. So it is the pump that pumps the air from the evaporator to the compressor. The compressor increases the pressure and thus increases temperature of the refrigerant that circulates through the closed system. It is often referred as the heart of the system because it circulates the refrigerant through the refrigeration loop. In the split air conditioning system typically used in light commercial and residential application, the compressor is located outside as part of the condensing unit. So it is outside, the compressor is found outside. But in large commercial installation, the compressor is, as I said, as part of the chiller. On large units, the compressor may be driven by a gas internal combustion engine or turbine, or also can be driven by electric, but usually now electric is the most common way to use a compressor. Expansion valve. By sensing the temperature of the evaporating or expansion valve, control liquid refrigerant passing through a small orifice, which causes the refrigerant to expand a low pressure and thus low temperature gas. This vapor compression refrigeration process relies on three physical principles. So, first is the heat moves from a high temperature region to a low temperature region. So, high temperature region is considered evaporator, then it will travel to compressor, and then will go to the high temperature region, which is the condenser. A change in temperature of a gas is proportional to a change in pressure in gas. That in a pressure increase result in temperature increase in the gas, and a pressure decrease result in a temperature decrease. So it is just basic that temperature increases, pressure increases, temperature decreases, pressure decreases. A change in phase result in the absorption or release of latent heat. Evaporation of a liquid result in energy being absorbed by the substance, and condensation result in the substance releasing energy. Now, this is the vapor compression refrigeration system. The system contains liquid refrigerant that is forced through an expansion valve, causing it to change into a low temperature liquid. The low temperature liquid flows through the evaporator coil, cooling the coils and extracting heat from the recirculated room air or indirect from as recirculated liquid medium, chilled water, that is used to cool room air. As heat is extracted, the refrigerant absorbs energy, increasing its temperature and converting it to gas. Then warm gas is drawn into the compressor, where its pressure is increased, causing the temperature to rise. The hot refrigerant gas then enters the condenser through where coil dissipate heat directly to the outside air and indirectly to a liquid medium, water, that carries the heat outdoors. As the gaseous refrigeration passes through the condenser, it condenses into a liquid, releasing latent heat. The liquid refrigerant travels to the expansion valve, where the process begins again. Cooling refrigeration capacity. Cooling and refrigeration system are rated in tons of cooling. 1 ton of cooling is the amount of cooling obtained by melting 1 ton of ice in 1 day. 1 ton of cooling is equivalent to 12,000 BTU per hour, or 3.560 thermal kilowatt. This unusual unit is from the day when ice was actually used for cooling. Ice has a latent heat of fusion of 144 BTU per lab, or 288,000 BTU per ton. Melting a ton of ice over 24-hour period or 1 day produces a cooling effect of 288 BTU per day, or 12,000 BTU per hour. Direct expansion equipment. Direct expansion, or DX, is generic term that is used to identify vapor compression refrigeration equipment having 2 or more components. One usually positioned externally, and the other usually positioned within the building, so it is internally. Site-installed refrigeration piping that is charged with a refrigerant connects the indoor and outdoor components. The indoor components consist of fan coil units or air handling units that are located in the room being air-conditioned, or located remotely in mechanical room. Some manufacturers produce external units that may be located internally, and in the case of these units, ductwork is connected to the outdoor atmosphere to reject the extract heat. The refrigeration system are in direct contrast to chill water system, in which cooling is achieved by circulating chilled water. So in the X, they are using chilled water. Central air conditioners. A central air conditioner is a DX refrigeration cooling system. It has 4 basic parts. One is a condensing unit containing the compressor, condenser, and expansion valve. A cooling coil, an evaporator, and in the handling unit of ductwork near the furnace. Ductwork to distribute the cold air. So ductwork is the one to responsible distributing the cold air. And a control mechanism such as thermostat. The most common type of central air conditioner is a split system. So a split system has the condensing unit containing the compressor, condensing coil, and fan and expansion valve located outside, and a cooling coil, an evaporator in the air handling unit or in the ductwork near the furnace located inside. The outdoor condensing unit is connected to the indoor evaporating coils by 2 copper wires. The smaller pipe is the liquid line, which carries the high-pressure liquid refrigerant from the condenser to the expansion valve. The large suction line, which should be isolated, carries low-pressure gas from the evaporation coils to the compressor. Figure 6.6, it is an example of a split system air conditioning system. So first, the return air from the hot air from the room will be travel to a tube that will go to a fan. Then the fan will releases the air to the evaporator, and the evaporator will cold that air and releases it to the main air duct, and the main air duct will be the one to supply air to the room, and the extra heat that are rejected will go to the condensing unit outside of the building. In this photo, 6.7, it is a condensing unit of a system, split system. 6.19, it is also a condensing unit of a split system. In 6.18, it illustrates that a one aircon could have one or more than condensing unit. 6.20 is an example of a building that has condensing unit at the roof. 6.21, it is a wall-mounted aircon. It is the inside parts of an air conditioner. 6.22, it is a packaged air-cooled condensing unit. On the next slide is a packaged terminal air conditioning unit, or the PTAC. It's a self-contained air-cooled DX cooling unit, example given, with integral compressor of evaporator and condenser, an optional heating unit, and an optional minimum ventilation intake. A PTAC unit contains all the four components encased in one unit and is usually located in the utility closet or an exterior wall. A wall-mounted PTAC unit is interchangeable. It fits in a sleeve or extends through the wall so outdoor air can be accessed. PTACs are used to heat or cool a single living space quietly and efficiently using only electricity. PTAC are commonly used in hotels and apartments, as shown in photo 6.21. So PTAC is not just only releasing cold air, it can also release hot air, or they are also calling it hot air conditioning. A rooftop unit, or RTU, is a type of PTAC unit that is mounted on the roof and requires adequate support by the roof structure. It contains of cooling equipment, air handling fans, and frequently gas or electric heating equipment that are self-contained in a single unit. Rooftop units can be installed at the ground level. Rooftop units are available in size ranging from 1 ton to more than 100 tons, 12,000 BTU per hour, or about 3.5 kilowatt, or cooling capacity. More than half of all North Americans' commercial floor space is cooled by self-contained, packaged air conditioning units, most of which sit on the rooftop. That is all for my part of this report. Thank you and God bless.
So, individual air conditioners. Individual air conditioners are usually known as room air conditioners. They are usually attached to the walls or the windows and are exposed to outside air. You can easily distinguish room air conditioners through the absence of ductwork or the pipes to distribute the cold air. So the individual room air conditioners have a range output capacity of 4,000 to 3,600 BTU and an energy ratio of 8 to 12. So for the performance ratings for air and conditioners and heat pumps. So air conditioners and heat pumps have the same capacity, are usually available with a wide range of efficiencies. So measures to rate the efficiencies of an air conditioners are, first, the energy efficiency ratio, or the EER. The EER is a measure of the instantaneous energy efficiency of cooling equipment. It is the ratio of the cooling capacity of air conditioner or the heat pump in BTU per hour to the total electrical input. Under industry specified, test conditions. So the higher the EER, that means that that air conditioner or that heat pump is more efficient. And this test or this ratio only applies to those with a cooling capacity of greater than or equal to 65,000 BTU per hour. The next is the Seasonal Energy Efficiency Ratio, or the SEER. The SEER is a measure of the seasonal cooling efficiency of an electric air conditioner or a heat pump using a standard cooling load and outdoor climate profile over a standard cooling season. It is a rating that denotes the total cooling of a heat pump during its normal annual usage and for heating divided by the total electric energy input during the same period. So the higher the SEER, the more efficient the air conditioner. So that is something that you need to look at when you are buying air conditioners or heat pumps. So again, this is only applicable to those with cooling capacity of less than or equal to 65,000 BTU per hour air conditioners. Lastly is the IPLV, or the Integrated Part Load Value. This is a seasonal efficiency rating based on representative annual commercial loads. It only applies to air conditioners with a cooling capacity of 65,000 BTU per hour or greater than or equal to 65,000 BTU per hour. So to better know which air pump or air conditioner will work very efficiently, the EER is the most efficient or the most preferred rating when determining which air conditioner or heat pump will operate most efficiently during full loading conditions or when you are using it to the maximum. And also, the SER and the IPLV are better indications of which air conditioner or heat pump will use less energy over the course of an entire cooling system. For larger buildings or for larger commercial buildings, central chilled water systems are used. So they are more complex than split or package DX systems. The systems typically consist of a central chiller to cool water. The chilled water is then distributed by the appropriate fan coil of air handling system. In central chilled water system, there is a thing called the chiller. A chiller is a large piece of cooling equipment which is used to produce chilled water. This chilled water is then used to extract the heat from outside the building. Chiller uses the vapor compression refrigeration cycle to extract heat from the water and eject it outside the building. This then produces the chilled water. There is a type of chiller, which is the absorption chiller, that uses a thermal or chemical process to make the refrigeration processes necessary to make the cold or chilled water. So the selection of chiller, either the normal chiller or the absorption chiller, only really depends on the availability, and there is no thing as more efficient or mas nice. So this picture, for the left one, this is a commercial size chiller. This chiller is a water-cooled condensing unit and the slender tubes are fluid-to-fluid heat exchanges. The one on the right is a condenser water supply and returned and chilled water supply and return lines on the rear of the chiller. On the rear of this one on the left, there is you can see the condenser water supply tubes. So the chilled water circulates to and from the chiller and cooling coils in air handling units, where it cools air. Condenser water circulates to and from the chiller and a cooling tower, where heat is ejected outdoors. As I've mentioned a while ago, most chillers operate using the vapor compression refrigeration process like the chiller. But there is what you call a mechanical vapor compression refrigeration chiller. So they consist of a compressor, the evaporator, the condenser, and the electric motor, a steam or gas turbine, or internal combustion machine, or engine to drive the compressor. These chillers use a compressor as a part of the vapor compression refrigeration process and are classified by the types of the compressors they use. So there are 4 types of mechanical vapor compression refrigeration chillers. These are the following. The first type is the centrifugal chiller. The centrifugal chillers have a compressor that acts like a centrifugal fan. It compresses the vapor flowing through it, spinning it from the center of an impeller wheel radially outward so that centrifugal forces compress the vapor. Some machines use multiple impellers to compress the refrigerant in stages. They have very few moving parts and are workhorses of the space cooling industry. The second one is the screw chiller. The screw chillers have a compressor that is positive displacement device in which the refrigerant chamber is actively compressed to a smaller volume. The rotary screw chiller operates by the twisting motion of two meshing rotors. The single screw compressor consists of a cylindrical main motor positioned between identical gate rotors. The screw or double helical screw compressor consists of two mating twin-grooved rotors. Rotary screw chillers are smaller and lighter than centrifugal chillers. They have fewer parts than a reciprocating compressor and are generally more reliable and usually found in systems rated over 2.5 tons. The screw compressor is a relative newcomer to the space cooling industry, although it has long been used for air compressors and low-temperature refrigeration. They led the market for small to mid-sized chillers. The third is the scroll chillers. The scroll chillers, from the name itself, they employ a rotating twisted rod as a screw compressor. Twisting of the scrolls compresses the refrigerant, increasing its pressure. They have fewer parts than a reciprocating compressor and are generally more reliable. The last type is a reciprocating chiller. A reciprocating chiller is used in small installations. These chillers use a reciprocating compressor, a type of positive displacement compressor that relies on the back and forth motion of a piston in a cylinder to compress the refrigerant. As I've mentioned a while ago, there is a chiller called the absorption chiller that does not use a compression. There is no compression of a refrigerant in this type of chiller because it uses a thermal or chemical process to produce the refrigeration effect needed to produce the chilled water. So in the absorption chiller, they take advantage of a chemical property called the affinity. The affinity is the ability of some chemicals to easily dissolve into other chemicals. An absorption cycle uses two fluids, diba? A refrigerant and an absorbent. An example of a refrigerant and absorbent is ammonia and water, and lithium bromide, and also water. So those are two examples. So the refrigerant and absorption chiller dissolves into an absorbent solution for which it has a high affinity. An electric pump pushes the absorbent solution into a generator section where heat is applied to drive the refrigerated vapor out of the solution and into the evaporator. Substituting thermal energy for mechanical compression means that absorption chillers are much less electricity than mechanical compression chillers. So mas efficient sila sa mechanical compression because they do not use a lot of electricity because they use thermal energy for mechanical compression. There are two types of an absorption chiller, the direct fire absorption chiller and the indirect. The direct fire absorption chiller, from the name itself, has a burner underneath it, and that burner runs on a natural gas or a fuel that is used to provide or produce the heat required for the absorption process. And the indirect fire chiller uses a heat or the steam from another burner, which is placed externally, not directly underneath itself. Next is chiller systems. In a typical commercial building installation, a central chilled water plant consists of one or several chillers that produce chilled water. This chilled water is pumped to one or more air handlers where it cools the indoor air. The cool air is then distributed within the building through a network of ducts. The ducts run to terminal units that control the flow of air to diffusers. The chilled water plant also requires several additional devices known as auxiliaries to move chilled water between the chilled water plant and the air handlers. In addition, the waste heat from the chilled water plant must be rejected to the outdoor air using air pumps and a cooling tower. Chillers are generally located in or just outside the building they serve. So this picture shows the diagram of the components and processes of a central chilled water system. So a chiller has a refrigerant flowing through its components as part of the vapor compression refrigeration cycle. The chiller feeds chilled water from its evaporator to a coil in an air handling unit which cools air. The chilled water is heated as it passes through the coil, so is returned back to the chiller to be recooled in the evaporator. On the condenser side of the chiller, warm water is pumped from the chiller's condenser to a cooling tower where heat is rejected from the condenser water to the atmosphere. Cooled condenser water is then returned back to the chiller's condenser. Hybrid chiller system. So from the name itself, no, hybrid, they use electric and gas chiller. So duha kabok ilang gina-use sa same plant. This can help reduce first cost and operating cost and can minimize the loss of cooling during electricity outages. Chiller operations in hybrid systems can be alternated so that at any given moment, the chillers that are operating are powered by less expensive energy source. So they can operate both on electric and gas, or if there is a power outage, pwede siya mag-operate only on gas, or pwede po siya mag-operate only on electricity and dili sa gas. For example, in an electric and natural gas hybrid chiller system, the electric chillers would only operate when inexpensive off-peak electricity rates are available. For example, mahal ang electricity rates. So, ang kana inyong chiller system, which is hybrid, it can use or it can run on gas. So, kung mahal ang kuryente, dili lang samo ang inyong air conditioner, dili sa siya mag-run on kuryente, pwede po siya mag-run sa gas. And also, when expensive pod ang gas, pwede po siya mag-run on kuryente. So, muna siya ang advantage sa hybrid chiller system. So again, there is a need to choose between which chiller performs best. So there is the performance rating of a chiller is determined in the following terms. So there are two. The first is the coefficient of performance, or the COP. The COP is the cooling output divided by the energy input, and the higher the COP, meaning the more efficient ang unit. The next is the kW per ton rating, or the kilowatt per ton rating. This is commonly referred to as efficiency. So, the lower the kW or the kilowatt ton rating, mas efficient ang imuhang chiller, because this is the actual power input to the compressor motor divided by tons of the cooling produced, or kilowatts per ton. Let's go to the use of multiple chillers. So, a chiller is most efficient when it operates at its rated capacity. For example, ang isa ka chiller, among yang max lang is 10,000. So, mas efficient siya kung imo jud siyang iadto sa yang maximum nga capacity. So, example, sa mall lugar, mas jud ako magpalit ka og gagmay nga aircon, tas imo siyang i-max. For example, dako nga sa isa ka stall sa mall. Kung luwag na ang stall sa mall, mas dili siya recommended nga magpalit kag dako para na nga stall, di ba? Mas tiada siya if magpalit kag daghan nga gagmay, tapos imong i-max tanan. Mas efficient na siya kaysa magpalit ka og big. Because as I've mentioned, a chiller is most efficient when it is operated near or at its rated capacity. So that's all for my part. Thank you.
Good day, everyone. I am here to tackle about our report. Air-cooled condenser. It passes outdoor air over a dry surface coil to condense refrigerant contained inside the coil. Evaporative condenser. It passes air over coil sprayed with water, taking advantage of the latent heat of vaporization to reduce the condenser temperature. Next is cooling tower. Expelled heat from chilled water system when water is cooled by directly or indirectly contacting the atmosphere. In cooling towers, secondary chilled water carrying heat from chiller moves through a series of levers and baffles. Sensible heat transfer, when the temperature of the circulating water is higher than the incoming outdoor air temperature. Latent heat transfer, when water is evaporated in a cooling tower. Entering wet bulb temperature, measures of the level of humidity and ambient air entering the cooling tower. Types of cooling towers. First is the direct or open cooling towers. It exposes the cooling water directly to the outdoor air. Second, indirect or closing cooling tower. Circulates the cooling water through the tubes of a coil bundle in the water tower. Next is forced draft cooling tower. It employs an air distribution system that forces air into the tower. Then, induced draft cooling tower. Operate by pulling air through the tower and use fans located at the top of the cooling tower. Next is the capacity of cooling towers. Package cooling tower systems are manufactured from range 10 to 250 tons in a single unit. Systems up to 1,000 tons are typical. Performance of cooling tower. In every cooling tower, there is a loss of water to the environment in the form of pure water, which result from the evaporative cooling process. Next is drift. Consists of small unevaporated droplets of water that becomes entrained in the exhaust airstream of a cooling water. Cooling tower. Evaporative coolers. Turn incoming dry, hot outdoor air into moist. Then, single-stage direct type coolers, or also swamp cooler most type use. Types of direct coolers. Number 1. Fixed fiber pad coolers. Have pads made of shredded aspen wood or synthetic fiber package in plastic netting. Second is the rotating pad coolers. Had a pad made of a rough polyester material sewn into a wide belt shape. Third is the rigid pad coolers. Have a stack of corrugated sheet material that allow air to flow through it like a pad. Next is indirect evaporative coolers. Similar to direct coolers, but uses heat exchanger that separate indoor and outdoor airstream and prevent moisture from being added to the indoor airstream. Next is two-stage direct and indirect coolers. Use air-to-water heat exchanger called pre-cooler that reduce the incoming air temperature without raising the relative humidity, then put the incoming air through a direct evaporation stage. Lastly is cool thermal storage. A system stored and produce chilled water or generate a phase or ice. As you can see in the diagram, it is a diagram of an ice thermal storage system. A chiller makes ice during off-peak hours, which is stored in ice storage tanks. The ice is melted during off-peak hours and used to make chilled water. Chilled water thermal storage. Use the sensible heat capacity of water to store cooling capacity. Eutectic salt thermal storage. Use the combination of inorganic salt, water, and other elements to create mixture that freezes at a desired temperature. Full storage strategy. Shift the entire on-peak cooling loads to off-peak hours. Last is the partial storage strategy. Runs the chiller to make part of the peak period cooling load and the remainder is met by drawing from storage. As you can see in the photo, a small-scale ice storage system uses off-peak energy at night to chill ice used for cooling the house on hot days. As you can see at the graph, it is a graph of potential savings with an ice thermal storage system. In this hypothetical example, smaller chilling equipment, about 250 tons cooling, can meet the 700 tons peak demand. And that's the end of our report. Again, I am Princess Girly A. Oliveira, together with my groupmates Jade Sultan and Jairi Ninu. Thank you and God bless.